Fast engines. This is a nice experiment for that.
I skip these. You can read it in the handout. It's about the standards for the drives. So something about standards and what you should do and what you shouldn't do. Read the manual. So here's something about switched inductive charges, loads. Sorry. So you may have motors or valves which are switched on with the circuit breaker. There are no requirements in terms of standards, because they're single components. But the point is they are reactive, so you've got charged energy, inductive energy. And if you disconnect the current, you get a high voltage and a sparking across the contacts. That's what you normally can hear on the radio when you've got a refrigerator that switches off. You can hear a click on the radio. Well, forget about the standards for the moment, but what happens if, these all standards, the load here, so I've got the current here, differential mode circuit. And what I'm going to do is I'm going to disconnect the switch. So I'm going to switch off the valve or the motor. And then the stored energy, half Li squared, so the current squared, is going to turn into half CV squared, so high voltage. The same
with a small pressure, yes.
Yes. As again as with the loop on the ESD experiment. So the voltage can go nowhere because it's open circuit and actually builds up across the contacts and it's going to produce sparks. And then, well, when you read manual, you can say, well, let's say 10,000 operations. It should be fine in terms of mechanical durability, but electrical, it's less, it's 1 million. And then probably with a resistive load, because when you've got the inductive load, the contacts are going to go, well, they're going to burn because of the sparking. So for inductive loads, it's very often questionable what happens. So if you do an experiment, what I did myself, so 60,000 times of switching of an inductive load, and then I measured the sparking, so each pulse actually is a spark, before and after this exercise. And then this is before, this is a need what we call EFT, electrical fast transient or burst. It's also found in immunity standards, so actually you have to test equipment with this kind of pulses. But after 60,000 times switching, it's much more sparks and much longer, and also a higher amplitude. So the EM emission is going to be worse over time. It's going to increase. Well, what you normally do is just provide coupling devices, so RC networks, freewheeling diode. So that's common practice, hopefully. Just to show you, I've got this pneumatic valve here. Actually two. One is without the coupling device and one is with the coupling. I'm doing a measurement now on my instrument cables. So I've got the current ground cables here. And I'm going to switch on valve and off. So increase the scale a little bit. So this is 24 volts, so it's more or less the same energy stored every time. And if I look at the smaller time scale, This. It's actually what we call the burst, so multiple sparking. Only when I switch off. When I switch on, there's no disturbance. Only when I switch off the inductor. Or with a circuit breaker AC. But just to show the effect of coupling, decoupling device, and I go back to this cable again. Like this. A bit faster. So this off, on, off. And then the same valve with decoupling, RC network. There's no noise. So it's €1.50 decoupling device across the terminals, and it's not producing any noise. The same for an AC circuit breaker. If I switch with the solid state relay on the zero crossing, so I actually wait with switching off when I get the zero crossing of the sine wave, then there's no noise. Yes. So, simple tricks to get rid of the switching noise. Yeah, well, how many? We've got 10 minutes? Because the most important thing to drink is coming along.
It's also very interesting for the written exam. Sorry. It's also very interesting for the written exam.
Well, a few things, yeah. So I'll go quickly through. So we spoke about environments. So this is, well, more or less automotive. This is medical, ships, trains. These all require different levels. And automotive is quite severe, I think, in terms of humidity requirements. So you're on top, together with the aeronautics industry and the military. Well, Fred spoke about cable classes, very sensitive. So what we normally do is what we call EM zoning. So we distinguish several zones: office, laboratory, production plant, telecom tower with lighting, or high voltage. And this is all fine because it can sit next to each other without any interference. But as soon as we connect cables, then we've got an interfacing problem, because we can bring disturbance from the telecom tower to the office. So we have to protect against the high currents coming in. And the same for the high voltage and also the most sensitive environments. So EMC is basically about EM zones, and that's why we speak about current barriers. Because if we build a current barrier here, metal plate, where we build all the cables and so on, we can actually get rid of the currents going in. So you can make a simple plot plan like this. So it doesn't make sense to make any current barrier here, because it has to be at the perimeter of the building or the perimeter of the cabinet or for the car. You don't have cables going to the car, maybe for charging, but that's all. But when you've got a box inside with electronics, you rather use shield cables and connect to the box. Well, it's all simple. You need some EMC spectacles to get a different look at engineering. So we don't look at the building and look at the number of doors or whatever. It's an X-ray exercise. We look what's inside in terms of rebar, so reinforcement, steelwork, because we can use this as a Faraday cage for lighting. Also,